In this lecture, I want to talk about the last example. We've done examples 1 through 5. One of those you did in recitation, and the most recent one was the consumption problem involving Bruce and his vitamins. The other ones were all mixture problems. Examples 1 through 4, including the one that you did in recitation, was a mixture problem. And this one again will be a mixture problem. This is example 6. Now, this time, rather than lay out the story in verbiage, I'm just going to immediately show you the mixture chart. So as I say, this is a mixture problem. It's some kind of a manufacturer. You can see that it's a manufacturer of paper. And the manufacturer makes 3 kinds: acid-free paper, medium-grade paper, and cheap paper, using 2 sorts of resources: cotton rag and wood pulp. Now, the recipes you can read off from the rows. For example, if you want to make 1 batch of acid-free paper, you need 3 tons of cotton rag and no wood pulp at all. I guess you know about acid-free paper. This was a problem with paper that was manufactured early in the 20th century. The fact that it was acid paper, that is to say, if you use wood pulp in making paper, then after a while that paper will react with the air and it will turn brittle, it will crumble. So if you look at books and journals from a certain era, you see that they seem to be crumbling into bits, and that's a problem in libraries and for preservationists. So that's why I'm assuming in this example that you're not using any wood pulp in making the acid-free paper. There are recipes also for the medium grade paper and the cheap paper, and also I'm showing you the profit you make for 1 batch of each. For example, the profit in making 1 batch of medium grade paper is $200. Now, this is again a mixture problem. It's exactly the kind of problem we've solved in all the other examples except the example involving the vitamins. And we solve it in the usual way. So given the mixture chart, we can write down the constraints. Notice that now there are 3 products, and therefore we introduce 3 variables, x, y, and z. And a production policy will involve specifying 3 numbers: a value for x, a value for y, a value for z. What are the constraints? The constraints are that x is greater than or equal to 0, that y is greater than or equal to 0, and that z is greater than or equal to 0. Those are the minimum constraints, together with 2 resource constraints for the 2 resources of cotton rag and wood pulp. Now, one thing you'll notice is that the constraint that we get for the wood pulp doesn't involve x at all, and that's because, well, in the recipe for making acid-free paper, you don't use any wood pulp. So there's no x in that inequality. It simply says 2y plus z less than or equal to 12. But notice that you read those from the columns, as always. From each column, you can read a resource inequality. All right, so now what would be the next step? The next step is to draw the feasible region. And now, suddenly, we realize there's a certain issue. We have 3 products. That means we introduced 3 variables. A production policy, therefore, involves specifying an ordered triple, and therefore we are really working in 3 dimensions. There are 3 products. We introduce 3 variables, and the feasible region is therefore 3-dimensional. Well, how do you draw it? Well, the answer is you're never going to be asked to draw that. That's a harder problem. To make a picture in 3 dimensions is a harder problem than to make a picture in 2 dimensions. I have done it for you. And it turns out that the feasible region is a certain solid. It's a solid in 3-dimensional space. It happens to have the 5 corners that I'm showing there. You might want to think of the x and the y-axis as being horizontal and the z-axis now being vertical. 4 of the corners lie in the xy plane with z equals 0, and then there's a 4th one up higher, 0, 0, 12. How did I find that? You don't need to worry, okay? So I have somehow worked this out, and I'm telling you that the feasible region is the solid with those 5 corners. It has corners, it has edges, it has flat faces. We call this a convex polyhedron. Polyhedron simply means many faces. Now, you have to wonder, oh, can we still use this principle that we've developed before? And the wonderful answer is yes, there is still a corner point principle. So if the profit formula is linear, then the maximum profit is achieved at one of the corners of the three-dimensional solid. And in this example, indeed, the profit formula is linear. We've assumed that you can make $400 for each batch of acid-free paper and so on, so that the profit formula will simply be 400x plus 200y plus 100z. So given that, and the fact that there is a corner point principle, we now know how to finish up the problem. This part of the problem you should be able to work out on your own. Namely, you list the 5 corners, and then you apply the profit formula, which I've already named. And now, since you're trying to maximize the profit, you would like the largest figure that you see in the table, and that is $2,000. And the way to achieve that is to go to the corner 260. That tells you that the optimal production policy is to produce 2 batches of the acid-free paper and 6 batches of the medium-grade paper. Don't produce any of the cheap paper at all. In general, when you're solving a mixture problem that involves 3 products, then your feasible region will be some sort of a solid. It will be a solid, again, bounded by flat faces, planar faces. All the faces will be as if cut out by a machete. They'll be flat, planar faces. Of course, they will intersect other faces, so that means they will turn out to be polygons of some sort. And I'm showing you here 4 examples that I've taken from various sources. The only perhaps misleading aspect of these 4 pictures is, with the exception of the one at the top, they seem to have some kind of symmetry or regularity. There's no reason to expect that in a general linear programming problem or a general mixture problem that you will have any kind of regularity like that. But what you always should expect is that you get some kind of a convex polyhedron. Now, why did we suddenly have to go to 3 dimensions? Well, the answer was because in the problem there were 3 products. There was acid-free paper, there was medium-grade paper, and there was cheap paper. So you can see the number of dimensions in which you need to work has to do with the number of products. Now, this may suddenly seem very worrisome. What does that mean if you have more than 3 products? What if you have 4 products? What if you have 8 products? What are you going to do? The answer is you have to work in that dimension space. That is to say, for example, if your mixture problem involves 8 products, then you will need to introduce 8 variables. Let's say the first 8 letters of the alphabet, A, B, C, D, E, F, G, and H, and then your feasible region will live in 8-dimensional space. Now, when somebody says that, that just sounds sort of ridiculous, perhaps, to you, or just totally frightening. 8-dimensional space is something that one can actually think about if one is simply thinking about working in coordinates. All you're doing is you're talking about all the possible ordered 8 tuples of numbers. And then you have to decide which of those are feasible. So it turns out that one can actually make sense of all of this. And in particular, one can even say what is meant by the word corner. I won't try to define that because now I'm just sort of giving you propaganda. We're not actually going to do any examples. But you can make sense of what it means to be at a corner of a feasible region. Very roughly, a corner is a place where a lot of the inequalities turn out to be equalities. If you think about the previous examples, you'll see always a corner was a place where more than one equation was holding. So it turns out that you can make sense of the word corner, and here is the wonderful, wonderful statement. There's still a corner point principle. So you can use it, and you can solve your problem, even though it involves thinking about working in a space that you can't visualize.